You can hear me? 1, 2, 3, loud and clear?
Yes, now we do.
All right, okay. So we will start the session on hydrology, CryoSat at the service of hydrology. One of the nice breakthrough of the additional mission objectives. So this session is chaired by Carina Nielsen. Thank you, Carina, for being here. And we have 5 talks on different subjects about inland water, but also a little bit of information about solid earth physics, a little bit of sea to land and land to sea activities in the coastal zone in the poster session. And so I would recommend everyone to attend the poster session and of course reconvene at 4 o'clock, which is the time for the most important part of this workshop. It's the wrap up, the conclusions, and that will be at 4 o'clock today. So let's start now without any further delay, and let me introduce Carina Nielsen to talk to us about the role of CryoSat in river level monitoring from space.
Thank you very much, Jerome.
And you have 25 minutes.
Yeah, thank you. Okay, so I will need to be given the presenter role because I cannot share. Okay,
yeah,
thank you.
Should be able to share now.
Okay, so I hope that you can see my screen now.
Perfect.
Good. So thank you very much for allowing me to talk here in this workshop here with CryoSat. And now running for almost for 11 years. And it was kind of my introduction into satellite altimetry, starting with this mission here, where I started working with satellite altimetry in 2013. So it has been quite some journey, and I'm happy to have been on it. So maybe let me start my talk by making some statement about why CryoSat 2 is amazing for hydrology. So if you look at my top plot on the left, you see a zoom in on in Colombia, but basically it could have been anywhere on the Earth. So what we see here is in all the dots, we see CryoSat 2 measurements in SAR-N, and these are overlaid with the Sentinel-3 track in orange. And this, I think this plot, or a similar plot, kind of show how amazing CryoSat is, because especially in hydrology, where the targets we look at are typically quite small, having this dense coverage is a key essential. And also with CryoSat, where we have these 3 modes, and especially SAR-N is important for hydrology. If you look at the bottom plot on the left, in the small insert, what you see here, I'm sorry, it's a bit small, but here you see also, you see CryoSat, the range corrected and position corrected points, but you also see the gray, sort of the nadir locations. So the great thing is that we can get measurements even though that the track is not directly over the river, which is so important in hydrology where the target is so small that we will have additional measurements. The dense coverage of CryoSat 2 enable us to, for example, when we look at a profile of a river, as you see here on the plot on the left-hand side, what we see here is how perfectly CryoSat is at mapping the profile of the river. On top, you also see the Sentinel-3 locations. But when we look at this plot, the altimetry map would definitely be an empty space without CryoSat. Of course, now we have ICESat 2, which is also have this more geodetic-like orbit, but also Altica, who is in a drifting orbit. So now we have more missions that can do this. The dense coverage of CryoSat is also very essential when we study lakes. I just did a small test where I took a subset of the database from hydrolakes, where I look at lakes between 20 and 50,000 square kilometers. When we look at how many how many lakes Sentinel-3 will see, it will be approximately 46% of the lakes, while CryoSat is able to map 99.5% of the lakes. Of course, some of the lakes may only be visited one time, but still, it is quite amazing. A very recent work by Alessandro Di Bella from ESA, formerly DTU. He has done started some amazing work where he took his swath processor from sea ice, and then we have tried to apply this for hydrology. So basically, we now can go in and extract more surface water elevations from one waveform, and Alessandro is now in cooperation with us here at DTU to form a paper about this work. The work that I will present to you here today is, yes, I'll come back to that in a minute, but it's partly funded by an ESA project, an open ESA core project, which has recently ended, the RightSat project, where the purpose was to estimate discharge from multiple different Earth observation sources. And my part here is on the altimetry part. We're lucky that we can continue the project, merged by another open core called Stream. So now we will try to fuse the two different methods in this continuation of the project. So what we have been working on is how to derive water level time series from CryoSat. And what you see here is a map from the Po River in Italy, and we see a zoom in where we can see a Sentinel-3 track, a repeat orbit, and then we have our CryoSat tracks at different locations on the river. When we have repeat missions, it's fairly simple to derive time series at these virtual stations, but when we have CryoSat, it's not so straightforward. And what we will need to do is to, instead of looking at a small area, we will need to look at a reach over the river instead. Some of the things or issue we need to consider when we are trying to combine data at different locations is, for example, what you see here is the Po River again. And then at the bottom plot, you see the elevation profile. And of course, when we have the tracks coming at different locations, we will both measure the surface, the elevation, the water level change, but we will also map just the topography. Another thing to consider is that the amplitude of the water level may vary along the river. For example, when we are close to the outlet, we will have maybe a smaller amplitude compared to further upstream. But all that will depend on the morphology of the river. So what we are trying to do here is to consider the CryoSat data. We view them as a time-space problem. So what we do is to take all the measurements and then we project them to the center line of the river, which will make all our measurements be a function of space and time. So in this study here, we have used CryoSat, but we also used all the other missions, or not all, but we have used Sentinel-3 and Altica. And what we do is that we consider data along a reach of the river as approximately 200 to 300 kilometers, but it will depend on the river itself. The motivation for this is that if we just look at a single mission, for example, Sentinel-3, which has a repeat period of 27 days, we are able to, and you can see this example here at the bottom plot. What you see with the gray lines is the frequency of the Sentinel-3 measurements, and what you see in orange and red is in situ gauge water level from the Amazon and the Po River. Sentinel is perfectly capable of mapping these large rivers, but when it comes to smaller rivers, it will miss a lot of the signal. So what we have tried here to do is to formulate what's called a state space model. And what you see here in the top part of the expression here is that we can consider a water level measurement as a function of an amplitude and a seasonal signal. So what you see here is sort of the alpha here will be representing the amplitude of the river, and tau will be representing the topography, and beta is representing a bias that is depending on the satellite, and then we of course have an error. The eta here is a process part of our model, and that is what you can see down here. So this is just a simple AR1 process, which when this row is between -1 and 1, it is what's called a stationary process. So it can kind of resemble the seasonal signal. So when we up here in our equation or in our expression here, we multiply it with the amplitude, we can sort of get a function for how we can represent the water level. In some cases, because you can imagine that our alpha part here and the tau part here, if we, in some cases when we have less data, it can be difficult for the model to separate these two terms. And then what can be done is to remove this alpha part here, which kind of represent that the amplitude can be different at different locations, and hence simplifying the model. So the model here is implemented in an R package called TMB, which I definitely encourage you to check out if you are working with these kind of models. When we have water level, when we're working with altimetry or inland water targets, we will have outliers. We cannot get around that, and that is typically due to that in the footprint we can have different water sources, we can have topography. So no matter how good a retracker we choose, we can never get rid of our outliers. So we need to ensure robustness in our model, and that can be done in different ways. We can have a more robust error distribution, but then your problem will can have difficulty to converge. So what we've done here is to, when we run our model and estimate our parameters, we run it iteratively. So basically in each iteration, we compare the observed water level with the model water level, and then we downweigh the upper P 100 percentile. And typically this P is a small number, between 1 and 10%. And of course, it will depend on the amount of outliers. So we've done some synthetic testing. So what you see here is a synthetic or simulated data for the Po River. And so the black circles represent the true outliers and the red crosses represent the outliers that we detect. So it at least seems to work here on the synthetic case. So so the data we applied here is CryoSat Altica and Sentinel-3 A and B, and now we also put ISAT-2 into when we are working with the rivers. We use a mask to extract the data. as I said, project the center line, project the data to the center line of the river. When we use this model here, we have to make some decisions. We need to say how many time steps we need because it's an AI1 process. We also need to say how many knots we want in the spline functions. Yes, the model here allows a lot of flexibility. So basically, we can estimate the water level at any place along the reach we're considering. So we're not restricted to having the water level at distinct locations. So on the plot I show you in the next coming plot, what I'll show you is where we estimated, or where we estimated the model at the location of the gauges so we can compare with in situ data. So first I'll show you an example here for the Po River. It's a bit busy plot, but the colors, so in red we have the in situ data, in blue we have the model result, and for comparison you will see a JSON, a close by JSON virtual station, and also in orange you will see a Sentinel-3 virtual station. What I like here about this plot is, even like in the early period where we only have CryoSat data, we are actually still able to capture most of the signal. But what becomes evident when we put more and more missions into the model, for example, in the recent years, we see now that we're actually able to capture many of the small peaks on the Po River, which has a very variable signal. Some more examples here for some other rivers. So we have, so I could say Po River is quite small, small in the sense that it's narrow, around a few hundred meters to up to a kilometer in width. Mississippi River is a bit larger, around, again, 600 to 1.5 kilometers in width. And here what we can see is for the Mississippi River, we have 2 stations. Still we can capture, with the model, we capture most of the signal. But again, of course, here we can see that Sentinel-3 is doing a good job, and of course, also JSON-3. Then we come to the Lena River, a bit the same. I would also like to put your attention to the Amazon River here, the Solomillos River. So of course this is a wide river, but still we can see with the model that given the fact that we use a lot more data than we have for just a single virtual station, we actually get the signal better. The Red River is the smallest here of the considered rivers. And you can see here again that we capture most of the signal. Yes, and the Red River here is an example of where we had to remove this amplitude part in order for the model to work. Some recent work where we tried to use fully focused SAR data and ISAT2. So the fully focused SAR data was provided with an upcoming service from ESA in the GPOD system, which is now converting to a new system, but have been kind to provide data for a small river here in the Mississippi basin. So this river here is just around a few hundred meters, and in many cases smaller than 100 meters. The ISAT2 data that we use is the ATL13 product, and then we have used gauge data to compare with. So when you see, so the result here again, we have in blue the model, and in red the in situ data. So we consider reach of 200 kilometers, and as you can see here, this river is very variable, and of course we cannot capture all the details, but still we capture the main signal. You can what's maybe important to keep in mind here is whenever you see these dotted dashed lines, this is the only time where we have data. So basically, we have very little data here, but still, it seems to work okay. So in summary, the geodetic orbit of CryoSat 2 is, I think, it's really essential. So I hope that when you design new missions, please always have these geodetic orbit missions. They're so important. With the reach-based method, we can make time series for drifting orbits, and we can incorporate several missions. And this helps us to make a better capture of the smaller river and the variability. So the method adds flexibility, so we can make the time series everywhere along the reach. And again, yeah, so it's important, I would say it's important both to have both repeat and also these drifting orbits. And promising result with ISAT-2 is that, or if we combine ISAT-2 and fully focused SAR data, we can go down and watch even narrow river. So with that, I would like to say thank you for your attention, and thank you to CryoSat for all the great science. And I'm happy to, if you have any questions. Thank you very much.
Thank you very much, Karina. We have a little bit of time for some questions. So Angelica wrote a question which concerned the last bullet of your conclusion slide. Maybe you could put back your conclusion slide.
Yeah.
But how narrow, you say less than 100 meters. But the question is, what the smallest width you would consider with CryoSat and also with ISAT?
Yeah. So with ISAT, yeah, we can definitely go to very small width. And I think with the fully focused SAR data that I applied in this test here, I think the sort of resolution was around like a measurement every maybe 10 meters or something like that.
With the fully focused SAR, the theoretical resolution that you can obtain is half antenna diameter, which is meter.
Yeah.
And 10, 12 meters would let get rid of
yeah.
Small 11.
Yes. Yeah. I think this case here, the smallest width was around 60 meters. So, but I mean, my take is always with altimetry is that you don't really know until you try it. So it is, yeah, just to try and test. Of course, as you could see from the result, I think what could help would be now that we can, if we had fully focused SAR also with Sentinel, where we have now the possibility with the code release from CLS. So that would definitely be the next goal, to try and incorporate that into the solution to see if it adds anything.
Okay. There's
Okay.
your conclusion about the drifting orbit is interesting. And I think we have a difference between a drifting orbit and a long repeat orbit. And
yes.
maybe say what is drifting is in fact a 30-day subcycle, which is drifting all throughout the year. And do you benefit from the fact that there's this 30-day subcycle in order to feed data into your reaches?
I haven't really considered that. Yeah, it's just, I think it's really the key that we have such good spatial coverage, because it really enables the possibility to kind of combine all the other missions, sort of the repeat missions in between.
Okay, Thank you very much, Karina. The next talk is by Christian Schwatke from Munich. And it's about the Tahiti database and dissemination system. And he will talk to us about the contribution of CryoSat to hydrological applications with this database, both LRM and the presentation is given by Daniel Scherer.
Yes. Well, thank you very much for having me. I'm Daniel Scherer from DGFI TUM, and on behalf of the entire inland altimetry group consisting of Christian Schwatke and Denise Dettenring, I show you here the benefits of CryoSat 2 to our Tahiti database. So what is Tahiti? Tahiti is a database for hydrological time series of inland waters, and we provide lots of different hydrological products derived mainly from satellite altimetry, but also from other remote sensing missions. And all of them are freely available from our website as is linked below. Our main product are, of course, the time series of water level from satellite altimetry of inland bodies such like lakes, reservoirs, and rivers. And to derive those time series, we use mostly altimetry data from short repeat cycle missions, but of course also from long repeat cycle missions like CryoSat with baseline D data from all the three modes, LRM, SAR, and SAR-in. And in the following slides, then I will show you the benefits of that. Additionally, we also provide water mass and time series of surface areas from optical imagery, such as Landsat and Sentinel-2, for currently more than 200 lakes and reservoirs. And there we fill data gaps caused by instrument errors and cloud coverage using a long-term water probability mast. And then we also combine those two products, and then we can generate partial lake bathymetry, hypsometric relations, and water levels based on the hypsometry, and then also time series of volume variations for currently 70 lakes and reservoirs. So first, I have to notice, of course, that since CryoSat has this long repeat orbit cycle, it's sometimes very hard to get meaningful hydrographs at one point. That can be hardly generated on CryoSat data because smaller water bodies are only overflown once or maybe twice a year. However, of course, the bigger the target, the more observations can be taken. Regardless of the water body size, CryoSat is always very useful to increase the temporal resolution of our time series in combination with other satellite missions. And here you can see in this figure how CryoSat bridges between, in this case, ENVISAT, SARAL, and Sentinel-3A. And also we get some very nice extreme events captured with CryoSat, which would have been missed with the long repeat cycle missions. And the biases between those all those missions are always calculated using a crossover calibration over the ocean, so we can then easily combine all the data. We also did a case study for the Mississippi River Basin where we compared different satellite altimetry constellations we performed. In blue, we show you the JSON and ENVISAT constellation, which we call the path configuration. And in orange, we show you what we call the current configuration, which consists of JSON, Sentinel-3, A and B, CryoSat, and the SARAL drifting phase in this case. And additionally, we also show only JSON and Sentinel for comparison. And in the figure on the left, you can nicely see the percentage of missed lakes, the remarkable number of missed lakes for the path configuration, but also when we use only Sentinel-3 or JSON. And then on the right, you can see how much lake storage is missed by constellations that the important important contribution of CryoSat and other long repeat orbit missions to detect almost all storage changes here. And I think this is very interesting, also compared to Karina's results. She showed only those lakes above 20 kilometers, I think, but here you can also see that below those 20 kilometers, a lot of data can be generated with the addition of those CryoSat 2 and Saral drifting phase data. And for the statistics, the water body was monitored if at least 4 valid overflights per year were detected, which is quite few, but on the next slide, you can see an example of such a lake. This is Lake Levon in Texas. And as you can see, it's only overflown by CryoSat, so there's no other altimetry data available for this lake. And also it's only overflown 6 times by CryoSat in the past decade. So I guess the orbit drifted a bit off. However, we can, on the other hand, extract 758 surface area observations from the Landsat missions on the right, and you can see here lots of variations. And this shows there must be lots of variations, of course, also in water level and volume, since this is also a reservoir, not just a lake. And so this sparse information from CryoSat can still be useful when we combine those data using an hypsometry. So the hypsometry, or surface area to water level relationship, you can see here for Lake Levon. On the left side, so small points in the graph show synchronous water level and surface area observations with a maximum difference of 10 days between these observations. So there are only 4 points left from those initial 6 CryoSat observations, just because there was no surface area available in the 10 days time frame. And to those observations, we fit a modified function from Strahler, which theoretical basis you can see here on the right, to the synchron observations. And this Strahler approach is very robust, fitting those hypsometric relationships, quite more robust than a polynomial fit, as you can see here, and of course more valid than just a linear fit. And using this hypsometry, we can assign each surface area observation, which bounds are shown here in the orange rectangle. So it shows our minimum and maximum surface area and minimum maximum water level observations. And when we combine this, then we can assign for each surface area a water level. And then we can sort our water mass by water level. And in this way, we can then estimate the lake bathymetry, of course, just above our minimum predicted water level. So everything you can see here on the left in gray is still unknown because the water level was not below this area. And in this way, we can nicely calculate volume variations for the lake, and also hypsometric water level time series. And I think this is quite impressive what you can get from just 4 CryoSat observations then in the end. So coming to rivers, we take also here a short look. I think this overlaps also a bit with Karina's talk. And here we can see a stretch of the Danube River in Serbia on the left-hand side, and on the right, all the available data from the short repeat cycle missions, ordered by time and location. And as you can see, the missions cross the river in a very irregular pattern. And for this river, it's still quite good, but for rivers that are flowing in the north or south direction, it can be sometimes really hard to get enough data within a smaller basin of your interest. And so this is quite limiting the hydrological applications, which may require regular distributed data. And then we can just add all the data from those long repeat cycle missions. So here CryoSat, ISAT and ISAT2, which I added here. And we can easily see then the improvement of the spatial temporal density. However, of course, we cannot just merge the data as simply as for lakes, as Karina also said, but because we have to keep the river topography in mind. And our former colleague, Eva Bergens, used an universal Kriging approach here to interpolate the data from CryoSat 2 with JSON2 and NVSAT data. And in this way, the probability to detect flood events for the Mekong River was increased from 40% to a number of 80% when we compare it to using only JSON2 and NVSAT data. Yeah, but though currently what I'm working on is an alternative, or you can also add this to the Kriging interpolation approach, is that you use predefined river reaches and bin the data into those reaches. And here we use reach definitions from the new and high resolution SALT database, which was distributed as river a priori data for the new SWOT mission. And here you can see the dashed lines show the reach borders, and the solid gray areas show reaches with disturbed flow, so small waterfalls or locks or dams. And in this way, we can create individual hydrographs for each of the reaches when we consider the slope of the reach. And the slope is also given in this SALT database from the Merit digital elevation model, which is an improvement of SRTM. But on the other hand, we could also use ISAT2 measurements to derive the slope, because ISAT2 is very helpful to get this slope because of its measurement geometry with 6 parallel measurements at the same time. And then when we just know the river distance between those measurements, we can also estimate the slope. Yeah, and then of course this would be quite helpful to then do again this hypsometric approach, maybe estimate the river bathymetry to a certain extent, and then continue there towards river discharge, of course. Yeah, so to sum it all up, CryoSat 2 is of course really helpful for us to improve and increase the number of data within Tahiti. It closes temporal and spatial gaps between the missions. And in combination with satellite altimetry, lake bathymetry, and volume variations can be estimated even from this sparse CryoSat 2 data. And for rivers, then CryoSat 2 improves the spatial coverage of entire river systems and enables the spatial temporal densification of water level estimates. Yeah. So thank you very much. Maybe I have some questions. And thank you for having me.
Thank you, Daniel. Any questions on Tahiti? Nothing appeared in the chat so far. I have a question. So you use the SWORD database. So what's in the SWORD database, and what do you use from the database?
Yeah, the SWORD database is really nice because it contains river center lines at a very high resolution derived from Landsat imagery, and it also provides. So I'm sorry. Oh, and it also provides those reach definitions and topology of the rivers, and then also those flow disturbations and so on. And so it's a really good basis for us to scale all our methods in the end.
A question just popped up. Will a concentration of 2 crystals provide full coverage?
I guess this is in regards of those first graphs I show. Do you mean this full coverage then? I mean we must analyze, of course, the ground tracks from those missions and compare them to the lake and river masks. But I think the more, the better.
Of course. The question would be is just enough? I mean, we cannot afford 10 or 12 yet. Okay, thank you very much, Daniel. It's a very interesting database, and it's nice to see it in over.
Okay, Jerome, do we have time for one more question? Because I saw there's an additional question. Do we have time to take that?
Yi Huang, how to remove the water surface slope from CryoSat, for CryoSat?
Yeah, basically, first of all, you have to know the water surface slope. So, example from a high resolution DEM or from ISAT measurements. And then when you have your reach center line, you can calculate based on the slope and slope bias, if you want to call it, and just apply to the location of the cross section.
Okay, thank you. We have caught up a little bit delay, and Karina can take over for the next presentation.
Thank you very much, Jerome. So I'll introduce the next talker, Philip Moore from University of Newcastle, and then now we will go into some more technical stuff. So he will be talking about analysis of phase difference and target detection and range correction using ESA-ESRIN data. So the floor is all yours.
Hello, can you see the screen? Is my PowerPoint, is it working or not?
Yeah. Now we see your screen. Yeah, perfect.
Okay.
So yeah, so just put it in full screen. It was in full screen just before.
Okay.
Yeah, now it's perfect. Thank you.
Excellent. Okay. This talk summarizes work that we've been doing at Newcastle University over the last couple of years. And here we want to use ESA-ESRIN data to see how we can correct for off-pointing in the cross-track direction. So the fundamental question we ask ourselves is, to what extent can CryoSat-2 ESA-ESRIN data be used to determine the location and, more importantly, to correct the height for non-nadir water reflections in the cross-track direction? So if you look at the schematic and imagine CryoSat is flying into the screen, then there's the two antennae in the cross-track direction, distance beta apart, beta being the baseline. The satellite has a non-zero roll angle, theta r. And the water reflector that we're interested in is at an angle theta to the downward pointing nadir. In ESA-ESRIN, antenna 1 transmits, is reflected off the water, and is received back at antenna 1 and antenna 2. So the reflected, the transmitted signal is coherent at this point. Now, because the two antennas are slightly further away from the reflector, then there's a time differential between receiving the signal, or equivalently, there's a small difference in distance. But as it's distance measurement, we can convert that to a phase measurement. So we're really looking at the phase difference between the received signatures of the signals at antenna 1 and antenna 2. So that's just really putting it in context. In this talk, well, can't avoid talking a little bit about ESA-ESRIN multi-look analyses. What we're interested here in is the power of the waveforms, the cross power between the received signals at antenna 1 and antenna 2, the coherence between those two received signals, and then derive the phase. As a proof of concept, we apply the method over the ocean. But more importantly, for inland waters, we have two corrections which refer to the range and to the location. And the whole methodology is applied to the Amazon near the gauge at Tabatinga. Well, this is a standard analysis for multi-look analysis. If you start with the full bit rate data, that is, you use the telemetry I&Q data. I'm not going to go through this. This is sort of been published before, and you can see most of the details in a paper ours back in 2017. But essentially, in the SARIN mode, 64 pulses are transmitted rapidly, and then the satellite waits for the reception of the reflected waveforms. Now, for each burst center, then there's 64 pulses transmitted. We then go through various constructions such as beam formation, and that is to steer to certain ground points. And these ground points in SARIN mode are distributed about 320 meters along the ground track. For each ground point, then, we'll have up to 60 looks from different bursts. And it's this combination of looks which gives us the multi-look waveform and also gives us the power and the phase. We have to correct for the slant range, the tracker and Doppler range corrections. Again, more mathematics, I can't avoid it. Again, it's really to refer to afterwards. So we have the power of the multi-look beam at each ground point. We use a weighting so that those closer to the ground point are given a slightly higher weight. But the weighting, or the summation, is over a maximum of 60 beams in SARIN. Given the two antenna received signals, we can form the cross power. And once we've got the cross power, we can find the argument or the phase between the left and the right antenna. We can look how similar the signatures of the received signal at antenna 1 and antenna 2 are by forming the, well, that should be the multi-look coherence, not correlation. Now, what this gives us, if you look at some very simplistic theory based on a narrow beam and infinitesimally small pulse duration, is that over a level surface with a zero roll angle and a homogeneous sigma naught, such as over the oceans, then the phase will be approximately equal to the scaling of the roll angle. Over land, we can immediately get the position of the water reflectors. Now, this is the proof of concept over an ocean. We have a north-south pass off the Amazon estuary, and on the right, the top are two waveforms. There's actually two on each plot there, the left and the right, but they overlap each other so well you can only see the one. Below that is the coherence, and below that is the phase. And what you see is that if you studied any other point along that path, then all of these plots will be very, very similar. We note that the coherence, you see that peak coherence at about bin 500, that corresponds to the sub-satellite point. That's when we're picking up the nadir. Right. Using the simplistic theory, we can calculate the roll angle from the phase, and the difference between the roll angle is given on the CryoSat geophysical data records, that's the one in the dashed line, and the one that we calculate is given by the solid curve. And as you can see, it's essentially 0. The divergence from 0 below 0.5 degrees latitude is when the satellite begins to pass over land. So if you look at the statistics of the point over the ocean, then the mean roll angle difference is very, very small, essentially not different from 0 at 95-degree confidence. So that shows us that the approach is working over the oceans and that we set up everything, all the software correctly. Now, if we come to inland water corrections, then we have 2 corrections. One is for the slant range and the other is for the geophysical location. If we just use pure altimetry, then the slant range L will be interpreted as the nadir distance. But that's incorrect. As soon as we know the cross angle, we can calculate del, which is the correction to the slant range to give us the proper nadir distance. We use a river mask. The river mask that we derived was from the shuttle topographic mission, and that's ours in red. We have compared that against other solutions from the Landsat probabilistic water occurrence, and we can see that there's pretty good agreement. It's not perfect, and there's areas there that we miss because the shuttle mission was in February, and February is near peak flow over the Amazon. So we come on to the Amazon near Tabatinga. Then we have one pass which crisscrosses the Amazon, and the satellite's going again from north to south. On the right, the first column is for a point which is with a large cross angle, so that the satellite is not at nadir, and on the left, the satellite, so the other way around, on one on the right is at nadir, the one on the left is off pointing. Now going back to the Google Earth plot, then the yellow point is where the satellite is over land, but is seeing the river at some cross angle. The red points are when the river is at nadir. And what we can see at nadir, we get a specular reflection. And if you go down to the bottom line, we can see that the cross angle at that point is about 0. When we're off pointing, we get a small peak round about bin 480, and that's a reflection in the nadir direction, but the main reflector is for the water. The coherence in all of these cases is about 0.8. And from the lower plot, we can sort of read off the cross-track angle. It's going to be about 0.2 degrees for this location. Now, this is the total stretch of the river we looked at. It's a total 293 kilometers, and you can just about identify the Tabatinga gauge as that turquoise point. So it's about 80 kilometers. We go upstream from that gauge and 211 downstream from that gauge. So there's a lot. The yellow points are again those where the satellite is over land, but we're able to get a river reading by using off-pointing. Now, as we heard previously, one of the major problems we have is how do we compare gauge data with altimetric heights over a large stretch of river, particularly when CryoSat is in a non-repeat orbit. Well, we've used near enough a similar approach. We've looked at the misclosure between the gauge and the altimetry by allowing for a datum offset, that range offset correction that I talked about previously, and then the gauge height itself, the gauge epoch, is corrected for the position between the gauge and the altimetric point, assuming that there's a constant velocity for the river. So assuming that a wave will travel downstream at a constant velocity. We also solve for a slope, a constant slope over the reach, and also for a correction to the roll angle. So given all our data points, we put it into a least squares solution and we solve for the datum offset, the river slope, the river velocity, and this correction for the roll angle. And these are results from that single pass I showed previously. The top plot shows the cross angle and the lower plot shows the residuals. The blue are when it's classified the river at nadir. The red is when the river is at some off-pointing angle. And we can see that the off-pointing angle can be as high as 0.5 degrees. But if you look at the residuals, this is residuals after fit, we've done a pretty good job at correcting for those. I should have said earlier that slant range correction at 0.7 degrees cross angle is equivalent to 60 meters. So at 0.5, we're probably correcting for something like 30 to 40 meters of slant range. So we didn't use this cross range correction, we'd be 30 to 40 meters out. And this is all passes. Again, you can see the cross angle. The red points are where we have a large cross angle, where off-pointing is used. The black is where the river is at nadir. And the cyan is where the river is at nadir. But even though we get a cross angle, the cross angle doesn't appear to be over the river. The fitted residuals are again below, and any signature due to the large cross angles seems to disappear. So again, we're pretty confident that we're doing reasonably well. We can look at this data in a bit more detail. Here we have the residuals plotted against the month of the year. And we see that most of the high residuals occur during months 6 to 12, that is June to December. That is the low flow season for the Amazon, and that'll be where our river mask has problems. Our river mask, remember, was taken in February, which is near high, so there'll be occasions there where the river is dry, where our river mask is saying it's wet. And this looks at the residuals. The blue curve is that range correction that we have to make. So we are making corrections for over 60 meters. We can see that it's a quadratic shape and it's centered on the roll angle. The red points are residuals where we have corrected for the off-pointing. So without correction for those off-pointing, we would not have all those red measurements. Black are where it's at nadir, and cyan is where the nadir point is over the river, but the off-pointing value is not. Now, on the right, we have a zoom in of the residuals between plus or minus 3 meters. So here we're looking to see how well we've done. And we fitted these residuals by a quadratic, and you can see that the quadratic has a minimum near the roll angle. The roll angle is about minus 0.17 degrees. So we're not doing perfect. You know, and we are investigating why we still have this residual signature. But it's only about 60 centimeters at most, and bearing in mind that we are correcting up to 60 meters, we think our range correction is accurate to about 99%. Again, this table, I'm not going to go through all of it, it's for you to look at later. The top row is all those points that were deemed acceptable by using off-pointing. We have accepted 4,460. The second row are those that we will use by the standard approach, only those where the river is at nadir. And we have, by this technique, increased the number of observations by 37.6%. The downside is that our correction procedure is not perfect, so that the RMS has increased slightly from 48.55 to 53.18 centimetres. The fourth row shows if we take the points where both the nadir and our reflected point are deemed to be over the river, then we get slightly fewer points than in row 2, but the RMS also goes down by 5 centimetres. So it shows the power of the improvement of correcting for the cross-track off-ranging. So I think I've given most of these points during the talk. We think we've done fairly well. We see a residual 1% signature in the height, which appears to be proportional to the difference between the cross angle and the roll angle. We're not certain what the cause of this is, but we're looking at more sophisticated models for the effect of beam width and pulse duration, but it might be something else. We don't really know. Should have said that the river velocity and slope that we get out are pretty consistent. The river velocity is 6.916 kilometers an hour, and the slope is minus 0.0344. I missed off the dimensions. That should be meters per kilometers. I'd like to acknowledge that the early part of this work was funded by ESA under the crucial contract. I think I've just about run out of time, so thank you very much for listening, and you can read some of the more details later. Thank you.
Thank you very much, Philip. That was a very interesting talk, and nice to see so many ways that we can derive time series from CryoSat. So yeah, I'd like to talk to a bit more about that another time. But I think we have time maybe for just one question, and there's one in the chat. So it's Paolo Cipollini asking, could you in your least square fitting go a step further and make slope and velocity function of R underscore G EF distance from the gauge? Or would the problem be then ill-conditioned, or perhaps just one of the two?
I would think we could compartmentalize slightly, perhaps break it down into smaller stretches. So instead of using just one constant slope and one velocity, we could probably introduce some relationship to the reach distance from the gauge, but it will become ill-conditioned if you try to do too much, and then you'll just be fitting the parameterization to the data, and that's the danger.
Okay, thank you very much. And with that, I think we should move to our next speaker. Our next speaker is Luciana Fenoglio from University of Bonn, and she will be talking about altimetry over rivers. So the floor is yours, Luciana.
Thank you, Karina. So I share my screen now. Sure. Do you see my presentation? Do you see my presentation?
Yeah, it's perfect. Yeah, thank you.
Thank you very much. So welcome to my presentation about our CryoSat data. So the goal of this presentation is to evaluate the CryoSat data to see what we can do with this in rivers. The reason, the motivation in principle for the work is that we got very good result in our area where we are working at the moment. We are working in the river in Germany, and with Sentinel-3, which is a repeat mission, we are very happy to see that we can get to 10 centimeter RMS compared with the tide gauge station. And our goal is not only to use altimetry in order to compute height, but we will have some time also to transform this height in discharge in order to use in model and so on. So there is really an application analysis that we want to do, and we want to understand, I repeat, how good is CryoSat due to this repeat, so long repeat. How can we try to find similar or comparable result? So this was the goal. So what we can do with CryoSat 2. Of course, we have to proceed in a different way. And in my outline, so I explained the motivation. Then I will introduce you some of, so we have 3 test regions that we generally work at this moment. And I will explain the methodology that we apply to CryoSat. This is completely different from the one that we apply to a repeat mission, as we saw in the last presentations. And I will show some results. So what I wanted in this analysis really to give numbers, because it's interesting to know what we get. And yes, and here you see, for example, the first region that we have considered, and it was already explained. We talked already about the SWOT database. So SWOT database is done in preparation of SWOT, and you see that the SWOT database exists, but sometimes doesn't go exactly where we want, and we have to also understand if we use it. It says it's not perfect. So in our methodology, we will use this SWOT database, and perhaps it could some of the reason why we get some other results. So in principle, we have additional data that we need in our analysis in order to evaluate CryoSat. So what I use as data. So we used this data in SAR mode and in SARIN mode. So the first 2 here are data both in SAR mode, but they are different processing applied. The first one is the unfocused SAR processing that and with a ray tracker that is called Samosa Plus, that is good in coastal region. You use a lot it, and that is we found out in the Rhine is very good also for river height. And then there is a new product in GPOD. This is the fully focused SAR that from ICIS that we evaluate in the last period, and I stopped in that also. So the third one is SARIN data that are available only in the Rhine. So in 2017, I asked ESA and to get this data, and then we started to look at it, and then I went back again. I will show you what we get. So in principle, we have since 2017. Tommaso Paniello was so happy nice to give us and to have it in the map. So we are always collecting in SARIN, but there are some probably with the data or the processing that they are not quite happy. And I will show you. Then we use the BFK river gauges from the national agency, and we use the SWOT database that give us the center line, latitude and longitude, the width of the river with a constant width, the profile. So this I prefer to call it not the slope, because the slope is changing with the discharge, but the profile is the mean slope, I would say, the mean profile. So the region that I consider are 2. So we have this Elbe region. So I just plotted the CryoSat tracks in the Elbe region, because otherwise, in order to be able to see the rest. And you see, this is Sentinel, and then we have CryoSat. This was a lot of more data, and this is the VESA. VESA was pointed out by ESA. At the beginning, they told us, please look for the fully focused SAR in the VESA, and I will show you why it was perhaps not a good idea. But so we have ESA, VESA, Elbe, and the Rhine. So the methodology. So I am quite new working in hydrology, but I try to understand what is sensible to do done. So we need a center line. So we have the center line from SWOT, and we have, as I said already, width, slope, and geoid. Geoid we can compute it. We need also the kilometer river that is useful, but it's not in SWOT. But you find it from the tide gauges, and then you can compute it yourself where it's missing. Then we wanted to know the virtual gauge at the center line, which is the intersection of CryoSat 2 with the ground track, and then we have to compute this. Of course, you have to hope that your center line is in the center of the river, and then you would have to check, otherwise you will have your virtual gauge not in the water. And then we choose a river gauge, and then we try to correct using the profile all the points in such a way that it would be if the station is at the tide gauge. We have not applied here this velocity, not taking into account the distance and the velocity to the propagation of the waves. This we have not yet done. And then we validate the constructed time series against the river gauges. So we have in principle, we wanted to consider the full time 2010-2020, but we don't have data for all this interval. We realize this working with the data. So something that is very important to remember in this methodology, sometimes is forgotten, I think, or not said enough. So we have gauge data. And what is important is that if we wanted to my understanding, if we want to construct the time series, we don't have an obstruction around the river reach, so it must not be a river which is regulated. Otherwise, you cannot make this nice time series projected at the station. And it must be long enough to cope with the space-time sampling. So it's a very simple methodology. So now we go to the data that we use. So the first region is the Elbe, and we use the fully focused SAR with the following parameters. So it's with at the end, I think the 200 Hz would be about 35 meter posting rate, and we use the retract of the threshold. And we projected all these things to the tide gauge Neue Dachau, which is after the, sorry, I am considering only the river. This means everything that is after Gestack. So Gestack is a Mauer, so something to stop. And before Gestack, you have the tides, and after not. So I consider only the part of the river. And if the first look that I had to the data, that is you find also in the poster, I think, of the fully focused, is to compare it, to compare between the fully focused and the Salvatore G-pod. And you see that in both cases, in the river, you have the river width principle, and you see that they are all on the same line, and you have much more data in fully focused because it's of the principle of fully focused. And this is done, for example, in Ottendorf, which is in the estuary. So here you have tide, but you don't see because this is an instantaneous moment. And this is in Gestack, which is the first part of the river that I will consider. And you see here, which is the type of the part of the river that I am considering. So I am considering this with between kilometers 500 something, and yeah, so it's about 60 kilometers. And here is Gestack, so here is the sea, and here you have Gestack, and here you have this Neue Dachau. And I will project this. So if you want to, I consider only 1 year from fully focused, because it was quite long to process, but also because, yeah, so I will show you only 1 year with fully focused, and 6 years with G-pod, because we had data from 2016. I was quite, I would say, happy to see that with doing this methodology, so projecting the things, the data at the station. I remember that it's very shallow, so I mean there is no much of error here. Yeah? this is the elevation change. It goes from 0 to 6 meter or 10 meter if I go until the end. But I was quite happy to see that the two time series that I produced from fully focused SAR and for GPod, they are quite similar, and they follow very well the time series of the tide gauges. The tide gauges is in black, and you see what we miss. So it's in gray, you see the evolution real of the tide gauges, but in black you have just a point which are at the same time. So the correlation, the standard deviation is not very good. Yeah, so we are not happy with this data, but it's also because I didn't use any. I didn't throw away the data at all. So it's and anyway it's a good, I would say it's a good result. We have not seen other values presented in this presentation, in this session, so I don't know exactly what the other find, but compare with the coastal tide gauges is of course not okay. But I think that we see the same signal, therefore it's positive. It seems that with the method is not bad, also because it relies on other things, other information, the slope and so on. So if I go now to GPod data, and I was able to use only until 2016. I don't know why. Probably there were no data before. And you see again what I showed before, and then you see this part only with GPod, so only with SAR data. Also here, perhaps we should eliminate some point, and then the statistic would become better. But you see that we follow somehow the tide gauge. So this is yeah. I was quite skeptical on the method, but it seems that it's okay. Now I will go to the second region. The second region is the VESA. And this region is, so the river is quite smaller, and the worst thing is that it's regulated. So I use as river, same methodology as before. I use as river gauge Petershagen. The slope goes now from 0 to 60 meters, so it's quite higher. So compared to this, it could be that this water is not very well, not very good. So this you need in order to do your time series. The results are very bad. But I think that also if you have bad result, it's important to show, because yeah, it's bad in the sense that the tide Petershagen is regulated, and yes, and also only up from time to time you see a maximum. Yeah, it's yeah. So there is no much change in the data. Interesting is that both SAMOS SAR and SAMOS and fully focused follow quite well the same the same pattern. This means that or there is a problem in the methodology, or but the data are similar from the altimetry. So in this case, I would say that the suggestion to check fully focused SAR near to the in this area is good if you look at instantaneous comparison, but if you wanted to do some hydrology, we have to solve the problem. Going to the Rhine, so in this case, it would be very interesting to have, for example, with Sentinel-3, we can in the formula that I showed you before, that we have the slope, so compute the discharge. You can, with altimetry, considering 2 points along the same track, you can evaluate the slope of the river, and which from altimetry at the instantaneous slope. So the slope is not constant, so it's important to have the slope. This will allow you to evaluate the discharge. So the Rhine would be a very nice place also for CryoSat to help us to evaluate the discharge if the data are good. So we have this here, this height profile. So it goes from 0 to 100. So it's similar to the one from the VESA. And the results are that sometime it passes. This is a tide gauge station. That is the black one, and the Salvatore here in near Mainz. So I have to say that I didn't use the center line method because because the center line, first of all, because the center line from SWOT is very often so not in the center of the place. So it means that we have to construct our center line ourselves. And this is for me very important also to point out, because we believe the center line of SWOT in the middle of the river, but it's also not. So we couldn't use the other method, and we use a method that we always use for Sentinel-3, and this gives this result, because there are some points which are completely off for 60 meters. So here in the previous presentation could be that is something with the roll and so on, but this means that the data as they are at the moment in GPOD cannot be used, and this is the result real-minds. So this means that this brings me to my conclusion that it was one's goal was really to show you what we get with the data. Perhaps some of you have a better method and we can find a better result. But the conclusion are that if we use CryoSat in SAR mode, we had a similar result from Foley Focus and from SAMUSA Plus. The accuracy compared with the tide gauges is not too bad. Can be lowered if we eliminate some data, and in the Elbe really we find something that has sense. If we use in smaller river the same data in a smaller river that is also constrained and is not a free river, then we cannot apply the method, and therefore it's also one of the reasons why the result doesn't match. Also, however, the difference were quite strange, so we have to look more carefully in the data. If we then use CryoSat, if we use CryoSat in the Rhine River, so we at the moment we cannot use the other method, the centerline methodology, and we apply the methodology that we are normally use with Sentinel-3, but it doesn't work. So it is because there are a lot of outliers. So perhaps we have to go back to tracking ourselves the data and to see if there is some way to cope with this, because it would be very useful. So the use of CryoSat on rivers is challenging to the not repeat mission, and we still have to understand something on the data. So I think that before merging with other satellite, I would like to understand what the satellite is giving. Perhaps it's quite interesting, but just need to change something in the methodology or in the method to apply. And with this, I finished my presentation, and thank you for the attention.
Thank you very much, Luciana. Maybe you can just leave your presentation on just for a while, because we have a question from Pierre Fabry in the talk, or in the chat, I'm sorry.
Okay. I cannot see both.
Yeah, if you go to the first slide, let's see here. In the first slide, where it doesn't work, it seems that there is a glitch in the data, and in parentheses, several distant points look consecutive. They are linked by a horizontal line. Isn't there a time or geolog issue here?
Which is the first view graph? Is this one? No.
No.
Yeah. Which is the first view graph? I had numbers. This is number 5. Just before Rhine. Before the Rhine. Before the Rhine. This one, yeah. Yeah, this one. This is the Rhine. Yeah. Yes.
Yes.
Yeah. What was the question?
He writes that it seems that there's a glitch.
This one, yeah, I've seen, yeah.
Okay, yeah, okay.
Yeah, but it is. But I don't think this was the reason, but I can check. But yeah, this was something It was something that was related to the time series had these things, but I think that it was something in the data, not in the result. But anyway, the amplitude is very big.
Yeah.
Yeah.
Okay.
Yeah.
Yeah. Okay. So maybe before we go to the next speaker, so okay, so what you could, because I checked, or we checked also with Alessandro when we are working on this SWOT processing, that this merit elevation model is not always the best. So maybe what you could try to do is to use ESA-ESRIN instead to calculate your slope.
But also ESA-ESRIN, I mean, I heard the discussion before, but ESA-ESRIN gives an instantaneous slope. So you have to make an average over all the time, and ESA-ESRIN is coming every 90 days. So I checked in the Rhine how changed the slope in reaches is very, very much. Yeah, so it's the slope is not constant.
Yes, but yeah. Okay, so we can discuss that at another time.
Yeah, it would be very, very useful. I think that anyway, we are working in the same project. Perhaps you can
exactly.
Yeah.
But okay. Yeah. But thank you very much, Luciana, for an interesting talk. Also enlightening us with the use of the fully focused SAR for inland water. So thank you very much. So Jerome will introduce our last speaker.
The last speaker is Li Guangyang. And the presentation is about climate-driven variation in lake level, in Tibetan lakes.
You see my screen? Okay. Hello, everyone. My name is Li Guangjiang. Formerly work at DTU. Recently moved to China, the Southern University of Science and Technology. In this talk, I will talk about Tibetan lake variations, decadal monitoring from CryoSat. Some background: the Tibetan plateau plays a very important role in water supply to the ESA large river systems, such as wait a minute. Okay, such as the Brahmaputra, Mekong River, and the Yangtze River, and so on, providing water resources for downstream people. While the lake, as the very important unit of the landscape, act as a low-pass filters of climate variability, especially in the Tibetan plateau due to the unique topography, as well as the less human activities. The figures shown here show you the temperature change during the past 40 years of the Tibetan plateau. We can see the climate warming is at a rate of 0.4 Celsius per decade, which is much higher than the global average, which is around 0.15 or 0.2 Celsius per decade. Therefore, this area is very important to study the climate change and also the lake dynamics, because the lake also regulate the local climate and also hydrological cycles. And they are expected to be very sensitive to climate fluctuations. Previous studies have intensively investigated the lake extent expansion over the Tibetan plateau. This figure shows you the lake area change between 1995 to 2015, and the size of the circle indicates the expanded area. We can see most of the lakes had been expanding largely over the whole Tibetan plateau. Statistically, we can see the lake area has increased by 26% in the past 2 decades, and also have some new lakes occurred during the past 2 decades. However, this lake variation is not homogeneous over these regions. Most importantly, although these studies show the lake's expansion is very significant, but satellite imagery only show the lake change in the horizontal dimension. We don't know the vertical change of these lakes. In that sense, we cannot calculate the storage change because the storage is much more important than the area change. That means we need something to calculate the vertical change of these lakes. Well, in recent decades, we have seen this climate warming. 8 warmest years on record has occurred since 2010. As shown in this figure, the last 20 years, we can say the climate is much higher than that in the 1880s. This temperature anomaly reference to 1880s, almost 1 degree in 2020, higher than 1 century ago. Well, in recently we saw this large El Nino event in 2015, 2016, and this event has induced large drought over massive areas in these Asia-Pacific regions. One recent study have looked at some of the lakes in the Tibetan Plateau. The study has shown that there's a drastic drop in the lake levels during this El Nino event. However, because this in-situ data is very few in only a few lakes is gained. So how these Tibetan lakes respond to this extreme event, we don't know. Here we can see this in 2015, the lake level didn't respond to the summer rainfall, maybe no rainfall in this year, but we don't know. We can see the big difference in 2015 and 2017, also for these 2 lakes. Well, in this study, we tried to figure out how these Tibetan lakes responded to global warming in the latest 10 years in terms of lake level. Well, we also want to understand whether these lakes behave homogeneously or only a few lakes respond to this El Nino event. Therefore, we use the altimetry to look at the water level change. Here is a bit about the CryoSat, because many presenters have shown you this CryoSat has very dense ground tracks crossing many lakes that provide us many observations. The large coverage provide us a new view to look at these lakes, because if you look at the dashed line for the NVSat ground track, only a few lakes are sampled by NVSat. But if you look at the background, this is the green lines. This CryoSat sampled many lakes. So this CryoSat provides an opportunity to look at the whole picture of the Tibetan lake change. Well, because the CryoSat work operating in this closed loop, it also has problem over this radial topography. I will talk to you later about this problem. Okay, here is an example. The onboard tracking issues over the rugged topography, especially the lakes surrounded by the high mountains. Here is the descending track. Here I show you the terrain topography beneath this ground track. You can see that here is the corresponding to the lake elevation. Well, this is the mountain areas. Well, when the satellite flying over the lake from the north to the south, we can see the range window is not aligned with the lake, but somehow hooked on the mountains. Therefore, this measurement is useless. Obviously, is a few hundred meters higher than the lake levels. Well, it's also depending on the ascending or descending. We can look at this as the ascending track. Here, from the satellite fly from the south to the north, then can say this should be fly this way. then we can say the satellite gradually adjust the region window to the lake area, elevations. Therefore, this data, of course, this is useful data. And we also, sorry. Also plot the waveforms. Here we can see this waveform corresponds to this descending track, and we can clearly see the waveform is very noisy, or basically it's just a background noise. Well, another one we can see the very clear peak corresponding to the water signals. Well, here is another example of the Lake Namco. This satellite, this is the ascending track. Here show you the waveform. Well, this shows the location of the measurement. At the beginning, when the satellite approaching to this lake, the waveform is very noisy. Should start again, maybe. No. But here we can see the corresponding stacks. When the satellite approaching the lakes, probably the range window is much higher than the real lake levels. You can see here, the range is much higher than the lake levels. Then this many of the loops stacks are not targeting to the lake level. Then when do the stack, the processing, we missed some of the useful, only probably the forward-looking stacks are useless. And when the satellite approaching to the middle of the lake, the range window is adjusted correctly. Then we see more stacks or looks are useful to generate useful measurement. Well, this we have another example, but I didn't show you here. In the satellite waveform, very noisy when the satellite flying over the mountain towards the lake. Well, but in the end, we can see here, even the satellite is very close to the lake shore, still have a very nice waveform. It's not affected by the topography when the satellite flying from the lake to the mountains. Well, here is the example of the here is the statistics after processing the data. Use the data between 2010 to 2019. We use the mask of a lake larger than 5 square kilometer. In total, CryoSat crosses more than 500 lakes of the Tibetan Plateau. Of course, we selected 262 lakes with the area larger than 10 square kilometer and at least 10 observations. Here show you the distributions of the number of lakes with the number of observations. The mean number of observations is 34 for these lakes. And of course, the larger the lake, the larger the number of observations. After the screening and the filtering, we calculated the long-term trend. We can show the Tibetan lakes, basically show all of the lakes show this rising, this positive rate. Here we show you the statistics. Of course, we have some lakes show this negative trend. Well, this figure also show you the rising rate dependence on the latitude. We can say basically it's positive. The north, the lake, the larger the linear rate, the changing rate. Well, the green ones show all lakes. Well, the cyan ones show those in the inner Tibetan Plateau. This table show you the statistics. Overall, we have 200 lakes. That is 76% of lakes show a positive trend. That is on the median rate is opened 2 meters per year. But the negative one is not very significant. Only 13 lakes show is a significant decreasing trend. But the median rate is quite small. This figure shows you the distributions of the lakes. As I said, the lake level change rate is somehow depending on the latitude. You can see here most of these lakes with significant rising are located in the north of the Tibetan Plateau. Basically, divided by the 33 degree north, we can see most of these regions, the lakes in these regions are rising. Only a few lakes in the south, in the Brahmaputra River basin, and here we can show some lakes with a decreasing trend. But it is not worth that all lakes with a sharp rising trend is that is larger than 0.5 meter per year or located in these areas. Well, we also calculated analyze the interannual variations. We averaged the annual mean water level, then we calculated the interannual variations. These 6 figures show the variation for the different groups of lakes by area. But we find that the trend is generally shows rising, then slowly is decreasing, and then have a sharp increase. All these lakes show the similar pattern, but they don't show a dependence on the lake areas. And most of the lakes, 80% of the lakes experience a sharp drop in this El Nino event. We can see here, lakes basically has a sharp, and this is more significant. And here we can see here. Well, we also have some other patterns. Some of the lakes, they here show you the location of these lakes. They are kind of decreasing all this time from 2010 to 2017. Then after this El Nino, the lake was sharply rising. Well, another group shows this continuous rising. These lakes are mainly located in the north, beyond 33 degrees. Then we also calculate the lake storage change. As I mentioned, the vertical information is very important to quantify the storage. Then we use the constant lake area. We calculate, estimate the lake storage change over the inner Tibetan plateau. The figure show you here is the blue one of the lake storage. And we also calculate the storage, the terrestrial water storage from Greece. Then we can compare how much this lake affect the regional terrestrial water storage. We can see this basically the terrestrial water storage dominated by lake storage, especially in these 2 years, 2018 and 19. And we also try to figure out how this lake change corresponding to the climate change. We calculated basically soil moisture, the actual evapotranspiration and the precipitation. Then we also plot the El Nino event. We can see this region is mainly dominated by the large-scale circulations. For example, the El Nino event is largely affected the terrestrial water stream, of course, affected by the reduced precipitation. Then we have this reduced terrestrial water storage change. But after the El Nino, we have the La Nina, then we have this more precipitation, then the terrestrial water storage is increasing, recovered from the significant drought. Okay, then I conclude this. CryoSat is very useful for monitoring lakes due to its superior data coverage, because the previous satellite, for example, JSON is not possible to cover all of these lakes. We can't get the big figure of these lake changes. We can only see 10 or something like that is lakes they change, or few lakes, but not all of these lakes. So it's very important to use this geodetic altimeter to monitor lakes. The closed loop onboard tracking has difficulty to position the tracking window over radial topography. That show you this may be a problem with the rivers located in the valleys, but also these lakes or these reservoirs in the very radial topographies. Then we should really be careful look at the data before the analysis. Then the climate variability play an important role in controlling interannual variations of lake values. lake levels over the Tibetan Plateau, we can see the El Nino event is a large affect the whole Tibetan Plateau. This CryoSat can help us to quantify the vertical change of these lake levels. Lake level is widely affected. Okay, I already repeat this. On average, this above normal precipitation during after this El Nino event result in a sharp rise of 1.22 meter. On average, accounting for 56% of the decade lake level rise. That is the median is 2.19 and the mean is 2.90 and the median is 0.85 meter during the past decade. This work has published on this in this Journal of Geophysical Research Atmospheres. And I think that's all. Thank you for your attention.
Thank you very much, Li Guang, for a very nice presentation. I think we have time. There's one question in the chat from
Yes.
from Mark Drinkwater. Is seasonal surface condition freezing observed to influence lake surface tracking? And does this influence winter season measurements when melt runoff is reduced?
Yeah, we were trying to look at this using CryoSat to look at the thickness of the ice, but over the Tibetan Plateau, basically the thickness of the lake ice is 20 centimeter, which is below the range resolution of the CryoSat, which is around 40 centimeter. That means just one beam, which cannot distinguish the lake ice, the thickness of the lake is reflected by the ice or by the water. But in this long-term trend estimation, we don't think it will affect the result. And also we applied a robust linear regression that is a iteratively reweighted least square regression approach.
Okay. Thank you very much, Li Guang. Yeah, it was very interesting presentation, and yeah, so you sure made a large contribution with all your work on CryoSat in many different studies. So yeah, thank you very much for that.
Thank you.
I think Jerome has, I don't know, he has disappeared, but so
No, I haven't
you're still
disappeared.
here.
I
Okay.
removed the video because of the bandwidth. I would like to thank Li Guang, because this really shows that CryoSat is a climatic satellite, because it's been flying for a long time, and even though it doesn't make measurements every 10 or 27 days or 35 days, it does allow measuring long time series and do some climate research. And it's really nice to see the behavior, the response to El Nino, for instance, in the Tibetan Plateau. So thanks so much. I'd like to remind that now you have some time for lunch, but then there's the poster session, which is not really posters. It's called interactive presentations. So you can all go into Brella. There are 4 posters available in the hydrology session, and so you have 100 minutes to see 4 posters. So this is really luxury. You can spend 25 minutes on each poster, and initiate discussions and so on, and reconvene, of course, for the wrap up and conclusion at 4 o'clock. So thanks, Karina. Thanks to all the speakers. And have a good break, a 1-hour break, until we all meet again in Brella. Thank you.
Thank you. Thank you very much.
Bye, everybody. Bye-bye.